This video is the beginning of chapter 16. We're going to be talking about acids and bases for a very long time. The next couple chapters are about acids and bases. So this first video is a lot of definition stuff. We have seen acids and bases in Chem 1, we've seen them in titrations, we've seen them in various situations. We're going to go down the rabbit hole and see how deep this goes. First thing we're going to do is redefine acids and bases a little bit. Up to this point, we've used the Arrhenius definition, where anything with an H plus is an acid, anything with an OH is a base. That is not wrong, but it's too specific. What we are going to be now using is called the Bronsted-Lowry, it's supposed to be an S, Bronsted-Lowry definition of acids and bases. So I don't know if this is one guy with a hyphenated last name or two people, I don't know, it doesn't really matter. Okay. So for this chapter, the way we're going to define things is an acid is any form of proton donor. Remember, we talked about this last semester, but anything that is an H plus, H is usually just a proton and an electron. If it's got a plus charge, the electron's gone, so it's literally just a proton. So when we say proton, we mean H plus. When we say H plus, we mean proton. They're interchangeable. This isn't drastically different from the Arrhenius definition. Not a big deal. Okay. Bases, we broaden the definition just a little bit. This is any form of proton acceptor. And anything with an OH minus, as like if it's a salt with an OH minus, would definitely accept this and form water. Okay, so great, it meets that definition. But it does broaden, pretty much anything with a lone pair on it can probably be considered a base. Okay, so let's look at an example. Okay. Most of the things we're gonna see take place in an aqueous environment. I don't know why I keep underlining everything, sorry. So let's look at an example. So HCl, if you dissolve it in water, I'm going to draw this as only a forward arrow because this one actually happens to only be a forward arrow. Some of these are going to be reversible, which is why we had the entire equilibrium chapter. What happens here is this, they both have H's that could be ripped off as H pluses, and they both have lone pairs. Technically, the chlorine's got 3 lone pairs. So you can't just look at, oh, it's got an H plus, so it's an acid, or oh, it's got a lone pair, so it's a base. It honestly depends on the situation. So here, it turns out that HCl is a better acid than water. So the water is going to have to be the base in this story. Okay, water is inherently neutral, but if you put it in the presence of a stronger acid, it can act as a base. What happens is the lone pair comes over and rips off that hydrogen, and then the electrons end up on the chlorine. And what we form is this basically has acquired an H plus because it ripped off the H but not the electrons. So now instead of H2O, it's H3O, and now it has a plus charge. And the Cl pops off as a Cl minus. Not a huge deal at the moment, but throughout this chapter, we're going to talk about this molecule a lot. H3o Plus comes up all the time. So I'm going to at least define it real fast. It is a hydronium ion. So basically, if you have H plus in the presence of water, it actually forms hydronium ion rather than just floating around as an H plus. Okay. Now I will tell you that these reactions that we're talking about don't have to be aqueous. Most of the ones we're going to talk about are, but they don't have to be. Okay. So for example, HCl can actually be a gas. I guess I'll draw the arrows again. And NH3, ammonia, can also be a gas. And it turns out that if you have these things next to each other, this will act as an acid, and this will act as a base. So even though there's no OH on this thing, it is going to act as a base. And what happens is, kind of like we saw up here, this lone pair is going to steal hydrogen, this will become NH4 plus, and then Cl minus is what's left over. But these things actually come together and form one compound. So you get NH4 and you also get Cl minus, but we never write it like that. We just write it as a compound. Okay. Honestly, if you had a container of HCl, even if it's dissolved in a solution, and you had ammonia dissolved in a solution, and you left them next to each other, the fumes, there would be HCl fumes and NH3 fumes. They would actually come together and form crystallized salt all over the place. Okay. But technically, this acted as an acid because it gave up an H+, and this acted as a base because it received the H+. Okay. This isn't complicated, but it is subtly different than what we saw last semester. Okay. So, try to get a new piece of paper. All right. So, let's look at what happens if you throw something like NH3 in the presence of water. I'm going to draw water like this because I want to be able to like show the arrows ripping apart molecules. Okay. So, just for clarity's sake, this is water. Okay. Well, this has a lone pair and it has H's. This has a lone pair, we haven't drawn it, but the oxygen has 2 lone pairs on it and it has H's. So either one could be an acid or a base, but it turns out, for reasons we haven't discussed yet, that this is a better base. So this is going to act as an acid. Essentially what's going to happen is this lone pair of this is going to rip off a hydrogen, and then the electrons will end up on the oxygen. Okay. This is actually a reversible process, which is going to make life a little bit complicated, but that's okay. And you end up with NH4 plus, because this stole an H plus because it is a base, and this thing lost an H plus, so now it's going to have a negative charge. You end up with OH minus. We need to throw in some new definitions here. If you took this base and ripped off a proton, which is what we did here, the thing that formed is now actually slightly acidic. So if you went backwards, it would lose the proton and become a base again. This is called a conjugate acid. I'll define these things in just a second. This was the acid in this scenario, and it lost a proton. Now this is a pretty strong base. This is the conjugate base. Okay. The reason we can visualize it like that is if we turned around and we took these things and wrote them as our reactants, what's going to happen now is this is going to be happy to rip off a proton, and this is going to be happy to give up a proton, so this is now going to act as an acid, and this will act as a base. And this will still be reversible because honestly all we did was reverse the first equation, and you get NH3 in water. Okay, but what happened is the acid lost a proton, so now this is the conjugate base. This was a base and it gained a proton, so now it's the conjugate acid. Okay. Yeah. Honestly, if you took NH4 plus and you put it in water, this will still act as an acid and the water will act as a base. Water up here acted as an acid because it was in the presence of a base. Here it's going to act as a base because it's in the presence of an acid. This is still reversible. Now, this is going to, because this is a base, this is going to, I guess I should draw the dots, rip off an H plus, and so this will go back to being NH3, and this will have gained an H plus, so it's H3o plus. Because this was an acid, if it loses a proton, it is now the conjugate base. And because this was a base and it gained a proton, it is now the conjugate acid. Okay, so let me kind of try to define a few of these things here. So the conjugate acid, acid is essentially whatever was your base on the left side After it steals a proton, it is now protonated. It has an extra H plus laying around that could be kicked off so it can act as an acid. It's essentially your base after it steals an H plus. Okay, this is a proton, so this is a protonated base. So like we saw here, this was your base. After it gets a proton added, the equivalent on the product side is your conjugate acid. A conjugate base is kind of the exact same but opposite idea. It's an acid minus the H plus. So up here we said water was the acid in this scenario. It lost an H plus, so OH minus is the conjugate base. And OH minus, up until today, was literally our definition of a base, so it makes sense that this would be a base. Okay. Same thing down here. This was an acid because it had an extra H plus to donate. It lost it, now this is a base. Excuse me. Which makes sense because we said it was a base up here, so this is the conjugate base. Water is acting as a base because it's in the presence of an acid. It gained an H plus, so now it's an acid. It's basically something that we said could be an acid anyway with an extra H plus, so it's definitely an acid. Okay, so a little weird. We sometimes keep track of things in terms of conjugate acid base pairs. I'm going to start abbreviating conjugate as CONJ. So conjugate acid base pairs. So for like the first reaction, basically NH3 was our base, and the conjugate acid of it is NH4 plus. Typically it's written like this. It doesn't really matter which one is the acid, which one's the base, like whether the base or as long as they're paired up, you're good. It doesn't matter that the acid or the base is on the left or the right. Okay, and for this scenario, water was the acid, and the conjugate base is OH minus. So these are the two conjugate acid base pairs for this first example. I can't get them both on the screen at once. So that's one pair, that's the other pair. Okay, but being able to keeping track of conjugate acid base pairs is really, really useful. We're going to do this pretty much continuously this chapter. Well, this next couple chapters. So, based off the trends we've seen, water can be an acid or a base. It is literally the definition of neutral, which means if it's in the presence of an acid, it will act as a base. If it's in the presence of a base, it will act as an acid. So, water is what we call amphiprotic. Okay? Basically, what it means is it can be an acid or a base. There's lots of molecules that are amphiprotic. Water is, by definition, the most amphiprotic because it's inherently neutral. When we talk about acids and bases, typically anything that produces an H plus is an acid, and anything that produces an OH minus is a base. So if you mix H and OH, you get water. Water is literally exactly half acid and half base. Okay? So another way to visualize that is, let's try that again. I'm gonna keep drawing water like this. Okay. If you have a base nearby, a base will usually have a lone pair. The water is going to act as an acid because the base is gonna steal one of the hydrogens. Okay. If you have water in the presence of an acid, acids usually have H's, so I'm just gonna draw the H part. Okay, 2 dots, that's not supposed to be there. All right. What'll happen is because this is an acid, the water will act as a base and it will steal the hydrogen. So depending on the circumstances, water can be an acid or a base. This is something we're gonna have to deal with a lot this chapter, these next couple chapters, so this is kind of the ground rules of how most of this chapter is gonna work. All right, thanks.